So before we jump into the mock images and the data reduction pipeline, I want to give you a brief overview for how the mock catalogs are made. So it's made with a semi-analytic model, and the sources are sort of forecast or predicted with a physical model. So this is what it will be like. So this is what the data that you're about to interact looks like in 3D space. You are sort of on the right of the cone, and then you are looking back in time. So this is a light cone that is traced by our sight lines, and you can see that there are galaxies that are sort of both color-coded and size-coded for their mass. Well, this is halo mass, actually. And then, yeah, so this is what the mock data looks like. And I'll go through the physics inside the model in just a bit. Okay, so this is a brief schematic diagram for what is happening inside the Santa Cruz semi-analytic model. So that's the model that we use to create these mock catalogs. So basically, we extract a collections of dark matter halo from a hydrodynamic simulation, so we don't have to rerun the simulations over and over again. It's really expensive, but based on the dark matter halos that are extracted already, we sort of build a dark matter halo merger history per halo, and then we run down the halo merger history and use this model to track how galaxies formed and evolved over time within the merger history. So the schematic diagram sort of walks you through that. So from a dark matter halo, we have an estimate for the amount of hot gas in there, and then there are several cooling mechanisms that track how these hot gas are cooled, and then the cold gas is partitioned into multi-phase gas, including a atomic phase, ionized phase, and then the molecular phase. Then the molecular phase is then used to track star formation rate, and that outputs the star formation history that we interface with a synthetic stellar SED model that gives you all the photometries that you play with in a bit. And also the star formation rate gives us the stellar mass of the galaxies and also the stellar feedback that goes back to reheat the cold gas, and sometimes it kicks out a portion of the cold gas. You know, the gas will be ejected, and some of them get reheated and become hot again and wait to be cooled again. So the SAM includes many more other processes. So this is just a brief collection that I want to tell you about, so you get a sense of what kind of physical processes went into the model, and the sources are made with this physical model. Okay, so this is the bigger picture. We also have black holes in there, but we did turn on and on black hole or AGN feedback mechanisms, and we show that it doesn't really do much at the redshift that CEERS is most interested in. But you can also see in the bottom that based on the star formation history, we sort of forward model those into the synthetic spectra, and then the photometry, both rest frame and observed frame. So we'll be able to find all of these predicted physical properties and the observable properties in the CEERS mock catalog. So I would like to tell you more about the physical model itself. So the Santa Cruz SAM is only calibrated once at redshift 0, and this is what that calibration plot looks like. So blue is everything that outputs from the model at redshift 0, and everything else, including light blue, cyan, are observational constraints. So the physical parameters in the model are actively tuned so that the output matches observations as best as possible. Of course, there are multiple constraints to match. And then what is unexpected is that this model output performed very well at reproducing the galaxy population at high redshift. So what you're looking at now is the stellar mass function at redshift 4 to 10, and the data points represent observed constraints we have from Hubble up to redshift 8. So we did not retune the model. It's just the physical model itself doing its own work, and then it produces a galaxy population that sort of reproduced the real universe very well up to redshift 8. And we see similar things with the star formation rate functions. So the star formation rates are also tested against the observations. And with a certain amount of dust assumed, the UV luminosity functions are also doing incredibly well at reproducing the real universe. So just bear in mind later when you play with the mock data, you can also, in the future, explore their connection with the underlying physical properties of these galaxies. Okay, so back to this light cone. It's important to keep in mind that this is how we look at the universe. Other simulations give you a box, and They are great to understand how the universe works, but for creating observations that, to create mock observations that can be directly compared with future observations, it's really important to have this cone construct, because we are now able to put galaxies across a range of redshift, but along our sight lines into a mock image. So in this image here, I'm going to show you just that. So on the left is the observed Hubble ultra deep field, and on the right is a similar field of the same size, but made with the simulated light current. I could have tweaked the color to make them look even more similar, but I didn't do that. So, but you can get a sense of how similar these fields can be. And because we have this physical model that extends to lower mass halos, we can now add predictions that contains galaxies that only JWST can see, and I enlarge this small portion to help you appreciate how in the same field, really, there will be so many more faint galaxies in the future JWST observations. Okay, so this is what the data set you're going to interact looks like. On the right, I show you a couple of slices that across a wide redshift range, going from redshift 4 to 10. The field is overlapping with EGS. The simulated field is bigger than the observed EGS field. So the simulated field actually spans a total of 782 square arc minutes, and it contains galaxies down to stellar mass of 10 to the 7 solar mass. So, and it goes from redshift 0 to 10. So you can sort of see these specs there in the table.